The speaker is Austin Nevin, who is our coordinator for the ICOM-CC scientific working group. And he's here today to talk about some of his work with his co-authors Sara Bellet, Gianluca Valentini, Rinaldo Cubedu, Daniela Gomelli. Austin is a researcher at the Italian Research Council. I think all of your co-authors are there too? Okay. And as I said already, he's the coordinator of the Scientific Research Working Group. He's also a council member for IIC, and he has a PhD and a Master's of Arts in Conservation of Paintings from the Courtauld Institute of Art, and a degree in chemistry from the University of Oxford. He's going to present results from this research as part of the Futurama project, which is a very interesting project that has a lovely web page, which I encourage you all to look at. This project focuses on the study of the works of futurist painters, their methods and their materials. But Austin's talk here today is titled Advances in the In Situ Analysis of 19th Century Paintings Using Fluorescence Lifetime Imaging. Thank you, Austin.
Thank you very much, Barbara, and thank you all for being here. It's a real pleasure to meet you and to give you this talk today. As Barbara said, this is work which has been carried out both at the National Research Council in Italy, specifically the Institute for Photonics and Nanotecnologies, which seems a far cry to art conservation, but it actually isn't, and the Politecnico in Milano. And I'm really pleased that we've already heard today about relaxation and about paramagnetism and about fluorescence, because all those topics are actually keywords for my talk today. So first of all, what is it that my group focuses on? As you understand from the authors list, we are multidisciplinary in our nature. The Politecnico is an engineering university. I am a chemist and a conservator, and many of my colleagues are physicists. And that is an ideal marriage, in fact. It doesn't necessarily bring much funding, but it's nice to be able to work with really talented people who have completely different backgrounds to my own. My group focuses primarily on the development and application of new instrumentation, new instruments, and new methods for the analysis of works of arts and for the analysis of paintings, for the analysis of sculptures. But indeed, the tricky aspect of our work is that it's not easy to compete with commercial companies, but we try to focus on techniques which might not have the applications that perhaps XRF could have in a larger context, but which actually do give us useful information for work in conservation. And indeed, today I'm going to focus on one of those techniques, which is fluorescence lifetime imaging. And here you see one example of work that has been done not on paintings, but on the David in Florence, and that immediately brings you to the conclusion that we can't bring David to our lab. Not only is he much too large, but he's much too heavy. And we also couldn't possibly pay for the transport or the insurance. And that is, in fact, one of the major reasons that the transportable, non-invasive techniques are particularly attractive to us, because we can bring them to the object or bring them to the painting. You also see another example on the bottom with my colleagues in the study of wall paintings, which I won't talk about much today, but that's another example of painted surface which cannot come to my lab and cannot come to a museum. And here's just an example of the type of analysis that we bring. Again, a false colored image where red means something and blue means something else. But we've seen some of that today already. And I'm just going to tell you now that unfortunately David's nose hasn't been blown for many years, and some wax managed to get in there when it was waxed and has not been cleaned. In fact, it was only water cleaned, so that's still there if you want to go back to look at it in Florence. So, to give you an outline of my talk, I will start with very basics about fluorescence. You all know about fluorescence, you use fluorescence, we've seen fluorescence today. And then I will talk about fluorescence imaging, lifetime imaging, exactly what it is, because it might not be something which you're familiar with. And then I will go on to present work that we have done on 19th century paintings. Much of the work that was done in the past on fluorescence lifetime imaging was actually focused on marble sculptures and wall paintings, but we actually have discovered quite interesting things about the pigments and the materials used in the 2 centuries ago in the last century, which is the really topic of this talk. And I'll present work, as Barbara mentioned, as part of the Futurist project, by an early Italian futurist painter, the father of futurism, and also another painting by Van Gogh. And I'll closer look also at historical pigments, because that's actually, we couldn't take samples, but we can look at historical pigments to try to understand a little bit better what we see. And of course, I'll give you some examples of future applications. Just so you know, this is my colleague Sarah with the red hair, and our device in Situ with one of the colleagues and coordinator of the project, Futurist project, Mattia Patti. So, what about fluorescence? What is fluorescence? Well, fluorescence is relatively simple. It involves the absorption of a photon and then the emission of a photon. We know that. We use fluorescence all the time in our work. And as David mentioned this morning in his talk with the British Museum, and we remember the Fayum paintings and also Egyptian blue, we can measure both the emission spectrum, that is what we see with our eyes usually when we turn on a UV lamp in front of a painting, but we can also measure the absorption spectrum. That's much more rarely done in conservation, simply because it's more difficult to have a tunable source, but one can do that. The important thing is what we see with our eye, and what we saw in the last presentation was the emission. And we can take a photograph of that emission, we can measure it with a photometer, and we can measure it with other devices. But one thing we can't see with our eye is how long it takes for this photon to come back down again. That's the lifetime. The lifetime is kind of like the relaxation that we just heard about with NMR, except in this case, we actually talk about the amount of time it takes for this signal to decrease in its intensity. And this is a typical exponential decay of a very simple fluorescence lifetime. Now, it's not very easy to measure this, and that's because this actually occurs on a very rapid scale. However, the important thing to remember is that the emission and the absorption spectrum are actually characteristic of materials. That doesn't mean they're unique, because many materials have similar emissions. That's why many varnishes look quite similar under UV light. That's why it's quite difficult to use fluorescence as an analytical technique on its own. We always have to combine it with something else. But the fluorescence lifetime is likewise something which is quite indicative of a specific material, and changes in fluorescence lifetime can give us information also about changes in the microenvironment of a fluorophore, and also in some cases can give us analytical results, which I'll show you today. Just another word about fluorescence lifetime. Here we have it in detail. If we look at the intensity of the signal that we recover from emission and look at time, we can see that with time, that intensity, when we turn the light off in a room, slowly, the exit signs in an old cinema or the fluorescence of a material might diminish. In fact, we know from UV photography that as soon as we turn the light off, we've got no more signal. The paintings don't usually phosphoresce, but fluorescence is what we're usually interested in. As I mentioned, the lifetimes that are usually associated with fluorescence of organic materials are on the order of nanoseconds. Order of nanosecond, that's the kind of lifetime we can, kind of pulse duration we can have from many lasers, but we also have picosecond lifetimes, and we also have picosecond lasers in labs now, which can measure very, very fast fluorescence decays, for example, amino acids and small molecules. In other cases, however, phosphorescence occurs, and that is when, instead of having a signal which decreases very, very rapidly in time, we have, it takes a little bit longer to make it down the slide from the excited state to the emission, and we then have millisecond or microsecond lifetimes. That kind of lifetime is something which is known as phosphorescence because it's not an allowed transition. And I mentioned earlier that the lifetime actually depends on the microenvironment. That means the pH, the polarity, the coordination of the fluorophore, and in fact, it's used often in biology for differentiating amino acids in different types of proteins. Different materials have different lifetimes. So that's very useful for us to know, because that means that we can use a technique based on lifetime to try to map different materials on a surface. However, that's not exactly simple, but in the lab, we built an instrument which could do that. The instrument is based on the use of a pulsed laser source, so that is not like this light here, which is not pulsed. We have a very, very rapid pulsed laser source, which you can see here connected to the telescope here with this red fiber. And that is connected to an instrument here, which is completely portable and transportable. both of them. And we then use a fiber-coupled diode laser. This is 355 nanometers, so that's not too far off what we use often in UV photography, 366 with a mercury lamp, for example, of a pulse duration of half a nanosecond. And coupled with this instrument, we have both a CCD, which is a scientific camera, and an intensifier here, which is a very rapid device which we can open and close on a scale of 10 nanoseconds. And this allows us the possibility of measuring many images very rapidly after a pulse is delivered through this fiber. And one of the major advantages of this technique, which I'll show you, is that we can acquire images rapidly. We can acquire a fluorescence image in a number of seconds. And as you well know, we can see that with our eyes sometimes, but to get a good UV image with photography often takes minutes. The other thing that is useful to know is that it's not necessary to have darkness. We can do this with ambient lighting conditions. And that makes a lot more sense when you're working on scaffolding, but also in museums you don't want to knock anything over when you have a painting on an easel like this. The other thing is that this technique yields fairly complementary information to UV fluorescence, normal UV fluorescence imaging, where you might use a lamp. So that's what I'd like to compare in the next slides. Just to go over the protocol that we use, we can visualize this in this schematic, which is rather boring, but I'm going to show you so you have an idea of how we interpret results. If we imagine a laser pulse here in pink, which is incident on an object with two different materials, which fluoresce in a different way, and shown the star and the blob, we can then take an image first at the very beginning, right after the laser pulse, which causes then the absorption and the emission. And then we come again a little bit after the laser pulse, and we acquire another image. And then we do that again. And you see towards the end, or the decay of this laser, induced fluorescence. And then we can use linear algebra, relatively simple. Like the computer does it, not me. And we can then create a lifetime map. This lifetime map here has different lifetimes in the order of 5 nanoseconds, for example. So this is this one, which took a little bit longer to extinguish. And this one here, which is rather fast, so around 2 or 3 nanoseconds, for example. And the power of this technique is actually the fact that we can discriminate between these two different blobs on the diagram. The other thing we can do is play with algebra and maths, and we can make another type of image, which is a vectorial image where we have another kind of false color representation, both of the intensity and the lifetime. And that's useful because it allows us to try to differentiate, again, in a different way, different surfaces. So first case study of our work was actually the application of fluorescence lifetime to 19th century paintings. And I should just step back and say that this is not something which we had done very often in the past, because we're a research institute, paintings are not part of our collection, and these have not received much attention in Italian museums. And in fact, it was a really nice chance that we had as part of the Futurama project, which is studying futurist paintings, to examine these paintings together with other scientists. And I think you'll hear a little bit more about the results from these paintings in other presentations in this conference. But the interesting thing about these is that these paintings by Victor Grubesi di Dragon were paintings which were continually reworked by the artist, and applications of new varnishes, applications of new materials, and he was never really satisfied with the paintings which he kept in his own collection. So one of the questions we had was, where is the varnish? Where are the organic materials in the edges? How many layers there are, and so on and so forth. We didn't expect that we would find the interesting results I'll show you now, but basically I'm going to just first show you where we looked at the painting. Now, in theory, we could have taken one image of the entire painting rather than look at details. But because we had a little bit more time, and because of the rapid nature of the technique, we actually zoomed in on specific areas so we could make the most of the analysis itself. The painting is relatively small. You saw that earlier on the slide. And we're talking about 25 by 60 centimeters, so more or less this size. And we decided to focus on different areas of the painting. Here you see different circular areas. The reason they're circular is twofold. First of all, we have a circular intensifier on the rectangular CCD, and we also can use a circular laser beam, which is expanded on the surface of the painting. And we chose these different areas to try to examine different questions that were posed to us by conservators and by art historians about the nature of the layering and the different materials on the surface. I should just start off, as I told you, we don't do this in the dark. We want first to see what has been done with UV fluorescence. This is an image taken by the OP feature, and we can see here that we have quite a lot of fluorescent material on the surface, and we have some relatively dodgy retouching at the bottom here, and some other areas of where we know this painting has been treated, even though we don't have many treatment reports about this. Now, just to take you back to the, what FLIM exactly does, fluorescence lifetime imaging, if we look here, and I'll show you those 3 blobs that we saw before, except this time they're details from the Lavandaya painting, at 0 nanoseconds, we see more or less what we see in black and white that we see in the green UV fluorescence I showed you before. After 20 nanoseconds, which is actually quite a long time after the laser pulse, we see that some of the areas are quite a bit darker, and after 100 nanoseconds, we see again this white area. Now that's a very long time in terms of the fluorescence that we would expect of organic materials. In fact, to my knowledge, there are very, very, very few organic materials which would have this type of behavior. Now, just to remind you, we can, from every single pixel in this image, we can extract the decay based on these images here. We take actually about 60 different images at different delays from the laser pulse, and we can then construct these decay curves, which are relatively similar to the ones we saw in the last presentation, and we can fit these curves with different exponential, mono-exponential we tend to use, because we can fit any curve with multiple exponentials, but we want to make it rather simple. And here we can see the differences between this darker area in the figure and the whiter area here, which continues to fluoresce for a long time. And actually, you can see that with the green here, that the signal never goes to 0. Now, why is that? How can we explain that? That's a good question. First, I'll show you one more thing I forgot. Here, if we took the rapid decay, this is the type of lifetime image we can build. We can just consider the very first 10 nanoseconds after the laser pulse, and we can see that we have two different basic groups of fluorescence. One, the medium-rich varnish, we think, on most of the painting, and the whiter areas here are showing up with a lifetime of around 5 nanoseconds. The varnish here is about 4. That's typical of the types of varnishes that we've seen in the past. If we then look at the HSV map, as I told you, we can represent that in a different way. We can see green instead of blue and so on, which might give us a little bit more information. But if we look, and if we compare this, though, with the UV fluorescence image that we get on its own, we actually see a lot more differentiation in the materials on the HSV image than we do on the normal UV fluorescence image. And here we have 4.1 nanoseconds, as I told you, about which we associate with a varnish. And we also see, with a longer lifetime, where we instead consider the longer curves, we see a completely different HSV image. And this HSV image, in fact, shows us we have a different material here, which we really couldn't see. I'll show you again this figure, this image in the part here. We don't really see a difference in the lifetime between this area and that. We see a little bit here, but if we go to the longer lifetimes here, we have a different material here, and we see a relatively long lifetime in the white paint. We think that's because they're different materials, and in fact, we looked a little bit closer, and with XRF, we saw that. We can also say that we have in this red area, in the greenish areas, a very long lifetime. A lifetime which is well beyond anything I'd call fluorescence. In fact, this is definitely phosphorescence. And the question is, how do we interpret that? And one thought we had is that we think it's a zinc-based pigment with impurities. And XRF analysis by our collaborators at the University of Perugia and ISTM, which is Professor Brunetti's group, actually did detect with XRF the presence of zinc. Say, okay, why is that interesting? That's a good question. I'll just show you a couple more examples from this painting, then we'll move on to the others. If we look at the areas of the edges, we also see that we can, on the bottom left edge, we can really well differentiate the areas where there are some varnishes, some second varnish layer applications, which give us richer images than we have just with UV fluorescence. And that was interesting, of course, for the genesis of these paintings. The other thing we can look at here is an area where we have the light-colored sky and green grass, and we see with the lifetime image compared to the fluorescence intensity that we have, again, a relatively long lifetime in certain areas, which could be linked, for example, to the presence of a different pigment. If we look here at this painting, there's a very long name, we see in the sky this pinkish color, which we also see in the HSV image of the fluorescence lifetime, and this is a medium-long lifetime, about 7 nanoseconds, and that's similar to the type of lifetime that has been reported for red lake dyes and pigments. So I'll move on now to another painting by Vincent van Gogh, which we studied, which is one of 2 paintings in Italy by Vincent van Gogh that we know of, at the Modern Art Gallery in Milan. And if we look at this, this is actually a painting on paper, but using paint rather than watercolor. And we have a lot of impasto on the bottom of this painting, but we also see quite clearly the use of pencil and pastels in other areas. Now, the fluorescence image of this painting was exciting because it was green, and we could measure this very green emission, which we saw in most of the white areas. And we thought, oh, okay, zinc white, fine. Except, actually, the emission here is not quite what we would expect with zinc white. We have 520 nanometers, that's really green. And it was really quite intense, according to our instruments, although we didn't see it so well with our eyes. Very broad emission here from the white areas of this painting. If we look again at the analytical results we get using the same technique, fluorescence lifetime imaging, at 0 nanoseconds, 5 nanoseconds, and then 10, and 100, and 1,000, we see something similar to what we saw in the paintings by Grubesi. In fact, what we see here is a very long lifetime, which is not related to the medium or the size or the glue which could have been used on paper. Rather, it is isolated in the areas where we have this white pigment. And in fact, we measured this and it had a lifetime of around 1.2 microseconds, which is very, very long, again. And this is a long lifetime which we didn't expect at all when we went to do the analysis at the beginning. And we can see, again, the same type of curve, decay curve, where areas from the face are shown in blue, and we have a very rapid decay at the beginning, and instead areas of the white areas are shown here in red, where we have a very long fluorescence lifetime. And I'm just going to skip this part, but only say that actually what we notice as well is that even when we have the white pigment mixed with other pigments, for example, the red, we think there's a mixture, or the yellow, we have traces of this very long lifetime in areas of the painting where we think that Van Gogh used the same white as he used for the headdresses. And we see again that this doesn't have much of effect on the, this is a very low weight on the total intensity, but that's because phosphorescence as an effect is rather weak. It's only when you integrate over a very long time that you'll see it. Now, what can we say about this? Why that's interesting? Well, first of all, we immediately thought, first of all, this could be a phosphor, like zinc sulfide. Zinc sulfides were the old TV phosphors. When you turned off the television way before I was born, it would continue to give you signal, and it would kind of slowly. Good. That was phosphors, typical materials used in industry, and indeed the first X-ray detection was done with zinc sulfide phosphors. Zinc sulfide is a pigment which we find associated with lithophone, but we know from literature that if you add slight impurities to zinc sulfide, you create very luminescent materials. So that was our first thought. And in fact, I wrote to Joe Barabee at the Macron Foundation because I noticed that he'd also published on the fluorescence of zinc sulfide and the discovery of a Bible of Mark which had very fluorescent green signal, which he thought was due to a forgery, and in fact it was. And he sent me some pigments from historical materials, which are actually from this country. And we looked at the historical photographs of different mines around New Jersey and the Acme mines in Franklin. And in fact, there's so many minerals in Franklin that there's one named after Franklin, franklinite, which is zinc oxide, zinc silicates, and zinkites, which all contain trapped silver. And in fact, there's so many fluorescent materials, you go online, type in frankite and fluorescence, and you have many, many different fluorescence materials, but they weren't all green. Many of them are pink and red and so on and so forth. But these are photographs from the late 19th century showing the kind of ores that were, the kind of smelting that was used to produce ores. And in fact, we believe that during the smelting of the pigments used both by Van Gogh and by Grubesi, impurities were introduced, which could give rise to this fluorescence. In fact, looking at the pigments that were sent to me from the Macron Foundation, we looked in the microscope and did relatively straightforward UV fluorescence imaging of the pigments inside the microscope, and we can see quite clearly in this zinc sulfide we have isolated fluorescence from different points. And in fact, this is the Acme mine, and this is the New Jersey zinc mine, and here we have a zoom. And we can really quite clearly see that there are areas where we have this green fluorescence, but also quite a lot of blue fluorescence from other parts, the same samples. And an explanation for this, for example, the green is that a copper ion substitutes the zinc in the zinc sulfide matrix, and this gives rise to longer-lived emissions. And it's very well known that the more copper you have, the longer the lifetime is, and this gives rise to an emission of about 530. Silver impurities, on the other hand, and as I mentioned, there are lots of silver ores in the Acme mine, give rise to another emission in the blue at 450 nanometers. And in fact, if we look at the different pigments that we're able to assemble from the late 19th century, we see that we have different types of fluorescence emissions. In this case, some which can be associated with silver, some which can be associated with the copper, and we also have, in some cases, the presence of manganese. Manganese is a common element, and in fact, this manganese signal is about 570 nanometers. This gives you information that's really important to consider also the spectral, not just the lifetime properties. And finally, I should mention that these pigments all had a microsecond lifetime, so very long lifetime. This means that we could, we really do believe that the signal we have from the paintings that we studied is from this type of dopant, so metal ions in a zinc matrix, zinc oxide or zinc sulfide matrix. The EPR results, which is quite similar in principle to NMR, demonstrated in these samples not only the presence of manganese, and you can maybe see that in the front, but not the back, but we have quintuplet here of signals of manganese 2 ions, but we also detect the presence both of copper and of silver, and in some cases of cobalt, which we know was added as a whitener to lithopone. Where could these impurities come from? Well, you saw those photos, so you can make a good guess. But just to remind you of the synthesis of lithopone as a pigment, it is made by barium sulfide and zinc sulfate. Sorry, barium and the barite mineral is often associated with copper impurities, but the zinc sulfate, which comes from zinc oxide or metallic zinc dissolved in sulfuric acid, could well also have impurities. But what we saw in the samples that we looked at is we did not have homogeneous samples. They were all very heterogeneous. And that, in fact, is what we have been seeing in other research published on these types of 19th century pigments. So as a conclusion, I'd like just to remind you that what we saw was what we thought was quite exceptional. But actually, it might not be that exceptional after all. And especially not if we're considering the late 19th century when these pigments were new synthesis methods and products were made all over the globe, not only in the States, but also in Europe. We believe that the emissions that we saw are due to the copper impurities, but XRF doesn't see them because they're really present in very trace concentrations of these impurities in the pigments. The lifetime imaging is very rapid, and in this case, we could reveal the presence of these emissions. Now, exactly what that means for conservation is, of course, the big question. We know, for example, here that this was an area which was lost and then filled in the painting. And the other question is, of course, well, what happens to this lifetime when these pigments are mixed with other media? We don't really know, but the fact that they're due to these impurities could also have different implications when we consider different stabilities of different 19th century pigments. And therefore, that's one of the reasons we'd like to focus on the degradation and also the further study of pigments, because it's very difficult to get hold of pigments which are quite as impure as the ones that we found. I'd just like to acknowledge the research which was funded in part by the Italian Ministry of Research, this Futurist project. The other work has been funded by other European funding and joint initiative between France, Italy, and Cyprus. The University of Pisa and University of Torino, and also Joe Barabee for the pigments, and the Gallery of Modern Art in Milano. And I'd like just to do a moment of advertising for EU members here, and also we're absolutely open for collaborations to US scientists and conservators for access to our labs to do work just as you might do with synchrotrons to come to our labs. If you want, you can talk to me about that later. And finally, I'd like to thank my group. and do micro-advertising for the Lacona Conference Lasers Application to Conservation of Artworks in Sharjah in a couple months' time. So thank you very much.
I'm sorry that we don't have time for questions, but in any case, you would have to wait until I had asked all mine, because I have the privilege of the podium. And, and there are so many questions from that very nice, very elegant work, and I think that maybe we'll be able to build phosphor screens from a variety of 19th century zinc oxide all by itself. But, so I would like everybody to thank Austin again for that talk.